I actually local. I help with the Atlanta Java user group. We run a big conference called DevNexus in the April timeframe, and we run a big JavaScript conference called Connect Tech. Has anybody heard of that one before? Okay, how many people have been to that one? Okay, for those of you who didn't raise your hand, there's still time to buy tickets for this year, okay? We also run North Atlanta JavaScript, among other things. And for my day job, I work as a developer advocate at a company called Azul Systems, which is in the Java and cloud space. It's probably the best way to describe it. But we're not actually going to talk about Java and, we're actually not going to talk about Java much, but I do need to plug my company for a second. We make the best performing Java virtual machine in the galaxy, as you can see here. How many folks in here are Java developers? Okay, good. How many people do JavaScript, just out of curiosity? Okay, that's pretty much. Anybody do like Python? Anyone still doing Perl? Let's get as esoteric as possible. No, okay. I used to do Perl. I still have nightmares about it. So we have an open source community platform at my company called Fujay, where you can go and publish anything you want. Doesn't have to be about Java. It could be about cloud and other stuff like that. So check that out, okay? So what we're going to do in this presentation is, first I'm going to spend some time talking about the philosophy around enterprise architecture for the cloud. And then we'll talk a little bit about like what cloud architecture actually is. And then we'll get into some design patterns. So this is actually a 5-hour course that I do. Obviously, we don't have 5 hours to do this. So I'm not going to cover all the patterns for data management in this session. But what you can do is, after I've done the introduction and I've covered a few patterns and you see how I explain it, you can actually find the video online. I did it earlier this year at a conference in London. So you can actually see the entire 5 hours if you're interested in learning about all the different data management patterns for the cloud. Okay? All right. So I already asked a couple of questions about who you are, like what you coded and stuff like that. How many people deploy to the cloud in here? Okay, that's pretty much everybody. How many people don't deploy to the cloud? Anybody? Okay. So you do on-prem stuff?
So my customers do.
Okay.
I'm a customer success manager, so I'm just trying to.
Okay, no problem. And I think you raised your hand also?
We have all virtual machines.
Okay.
Not cloud.
Okay, so out of all the clouds that people are deploying on, who does AWS? Okay. How about Microsoft Azure? Okay. Google Cloud Platform? What other clouds are there? IBM Cloud, anyone use that? No, probably not. DigitalOcean, it's kind of a cloud, but doesn't have the level of automation that some of the other ones do. That's good. This gives me an idea of what different platforms you build on. I'm going to try to not make specific references to AWS or GCP or any specific functionality on those, because this is more an architecture presentation, and we are going to specifically talk about data management in the cloud. So. And again, what I want to start with is just a basic idea of what it means to go from on-prem or however we used to deploy things onto the cloud. Okay, so I think the key thing that I like to think of when I'm designing and architecting for the cloud is something called elasticity. Right? So when you are typically deploying into, or how you used to do it, when you deployed into your own data center or whatever, you had to wait a long time to get provisioned any kind of service. Usually it was bare metal, right? So back in the good old days, you would literally pick up the phone, call what you would call a systems administrator, and say, hey, we need to deploy this app next week. And then they would gristle a bit and say, well, maybe we can get it ready for you next month or some crap like that, right? So, but nowadays what you can do is you can literally go onto AWS or GCP or Azure, click a few buttons, and boom, you have a virtual machine that you can deploy. And of course, you can do all this programmatically. So you don't actually have to do it manually. You can write a Terraform script which will build out your whole infrastructure for you if you want, okay? So this is part of what elasticity means. So let's talk about how we design for elasticity, because I think this is the important part of it, right? Everyone knows how to provision stuff for the cloud, but how do you actually bake into your application and your application's architecture that idea of elasticity and get the most out of it and also not provision too much? Right? Because then you run into problems. Because anyone who deploys onto AWS knows that, don't worry about it too. It's fine. Okay. So when you over-provision something, it gets very expensive very quickly. For those of you running on AWS, actually any cloud platform, I don't want to single out AWS, it is not cheap. So I saw actually just yesterday, a friend tweeted that I'm running some stuff on WordPress and it costs 25 bucks a month on WordPress.com. And then he went through and itemized how much it would cost on AWS. And it was nearly triple that for just running a WordPress site with the database and a virtual machine, et cetera, et cetera. So it is expensive. So this is part of the things that I like to tell people when we talk about the cloud is you have to be very careful not to over provision because it can get very expensive very quickly having resources that you're not using, okay? So the other thing that we have to think about very deeply when we're building for the cloud is we have to have this idea of horizontal scaling always in the back of our head, okay? So what does that actually mean? Okay, so let's talk about that in just a second. But when we think about horizontal scaling and elasticity, if any part of your cloud architecture is not architected for the cloud, it doesn't have elasticity in mind, then you're doing it wrong. You have to go back and look at, okay, maybe my database is very static and doesn't necessarily need to scale, but when you do need to scale it, it should be something that you can scale in an elastic manner, i.e. you can push a button that automatically goes up in 50% in capacity or whatever you might need, right? All right, so there are three basic tenets when you're thinking of elasticity. The first is your compute power, elasticity in the network, and of course, elasticity for data. And we're going to focus on the data part today and look at some of the different patterns around having elastic data, scalable, how do you provision for, how do you build for horizontal scaling, et cetera, okay? And I've already covered some of the points as to why you need to be elastic, right? It's for cost savings, it's for having the most efficient architecture, et cetera, but this slide nicely summarizes it, I think, right? So we already talked about cost, but I think the second bullet is also equally as important, is having the ability to be adaptable to different needs at different times, okay? Because nobody has the ability to just say, okay, we're always going to run at this level of load across our servers or this many requests, right? What happens in every application is that your load or the number of requests always goes up and down during the day or during the week or whatever however your application is structured, okay? The other thing I like to tell people is when you go to the cloud and you are building in an elastic first way, you have this advantage of having time to market, right? So you don't have to wait for servers to be provisioned. You can write Terraform scripts that will automatically provision everything you need, and you save a lot of time. You can get your app deployed faster, right? And you can actually bake in that idea of cloud-first thinking all the way at the very beginning of developing a project or starting a project, okay? And that gives you that time to market advantage. All right, so one of the key pitfalls when folks are building for the cloud is they generally don't consider their data tier to be something that's elastic, right? So everyone talks about Kubernetes, for example, nowadays. Does anybody not know what Kubernetes is? Okay, so Kubernetes is is this being recorded, Utsu? Yeah. Okay, Kubernetes is a framework and a platform for building elastic applications. In my opinion, it is extremely complicated, right? I'm not the only one who thinks this, okay? It's very complicated, and you can spend like your entire work life trying to build for Kubernetes, and you don't have to do that nowadays. We'll talk about some options for not using Kubernetes later in this presentation. But the key point here is that when you're building for the cloud, don't forget about having proper elastic scaling for your data tier also. Because a lot of people think it's very hard, and it is hard. It's not easy. It's harder than just throwing Kubernetes at something or using something like Google Cloud Run to do auto scaling, et cetera. But we'll get into that in a few minutes, okay? So when we think about data in the app tier, we want to be able to scale more efficiently, and we want to do horizontal scaling as much as possible. Horizontal scaling is the idea where you add essentially extra compute power in a horizontal way, which means that you add more servers typically. Okay, vertical scaling, which I'll talk about in just a second, is when you add into an existing virtual machine more memory, more CPU, et cetera, et cetera. Okay, so let's see what that actually looks like. Well, we'll get to that in just a second. And when we think about data, of course, in today's world, we generate lots and lots of data. One of the things that was said a while ago, a few years ago, is people used to say data is the new oil, right? You shouldn't keep all this data around forever because it can be a liability. I'm not sure if I completely agree with that sentiment, but I'm sure most of the folks in this room have heard that you have to be careful what data you keep, because you don't want to keep everything. It can become a liability over time. Not just from the cost perspective of having to store it forever, but also what do you do with this data, and is there any security implications with keeping it, et cetera, et cetera. Okay, so let's talk about horizontal versus vertical scaling, because this is the basis of thinking about an elastic architecture. Right? Again, when we're thinking about vertical scaling, what we do is we say, okay, we have this application, it's running on this virtual machine in the cloud, and we need more capacity. So what are we going to do? We're going to add some extra CPU, we're going to add some extra memory, and so we're going to scale up that instance vertically. Okay, and that's what we did for years in the industry to get more capacity out of what we're doing. And eventually we figured out that that wasn't a great way to do things, because it took a lot of time, and those resources are now locked into place. So what do you do as a developer? When you provision something, you always provision for the worst case scenario. Actually, that's not the best way to say it. You provision for when you're going to have peak load, and you don't have peak load all the time. Right? We were talking about how your load or request goes up and down over time, so we have to consider that. If we do vertical scaling, we've locked those resources and we're always paying for them. Okay, so it becomes a cost issue also. Horizontal scaling is we add more servers. So we scale this way instead of scaling up by adding more CPU and other types of horsepower. Okay, so we talked about vertical scaling already. And let's think about the cost of these two things. Not everything is about cost, to be honest with you, but I do like to talk about it a bit here. All right, so this is a very badly drawn diagram by me. But one of the issues with vertical scaling, which is on the left here, is how much does it cost to get increased capacity for your system? Okay, so what happens with any kind of virtual machine, or even your laptop, for example, is that at a point, you exhaust the amount of resources available on that machine, so you hit that curve going up where it costs more and more and more to do more work. Whereas with horizontal scaling, what we get is we get mostly a flat line after we hit an initial penalty we have to pay for doing horizontal scaling, right? So you can see I've drawn two little lines there that show initially when we do horizontal scaling and we add more servers to get more capacity, there's a little bit of a penalty to be paid, right? What do you think that penalty is when we're doing horizontal scaling? What are some of the kind of overhead, other things like that? Anyone want to take a guess? It's not a trick question. I have trick questions later, but this one is not a trick question.
Cost of just spinning up new instances, I guess.
Some of it is the cost of spinning up instances. That's a good answer, right?
Coordination between the services.
Right. That primarily it's coordination between your horizontal scaling stuff, right? So when you add in a second server, you have one server, you add a second one. Now there has to be some crosstalk between these two servers. So you're putting extra network, extra load on the network, et cetera, et cetera. But as you scale out further, what happens is that line becomes more flat and you're not necessarily paying that much more of a penalty, okay? So anyways, this hopefully gives you an idea of what that vertical versus horizontal scaling is and why we don't do vertical scaling nowadays if we can help it. It's better to scale horizontally, but not necessarily always, right? So when we think about provisioning a server, how much CPU do you give it? How much RAM do you give it, right? All those things make a difference. But just in general, when you start going above, let's say, 128 gigs of RAM and 16 cores, you have a lot going on in a single instance. And the operating system itself will start getting pressure because of everything that you're doing inside of that specific instance. I also give another presentation on performance tuning for the cloud. And one of the things that we think about when we're talking about performance tuning is it's great that you've added all this extra CPU, but you reach a point of diminishing returns even once you go past 16 or 32 cores on a machine. Okay. Anyways, don't want to step over Utsu. Okay. So the other way that I like to think about this is in terms of requests per seconds per CPU, right? So this is just what I was referencing a second ago, right? As you add more and more CPUs, what happens is you no longer get that linear kind of scaling, right? So the left is, or the y-axis is the number of requests, and the x-axis are the number of CPUs, right? So at a certain point, even though you're adding more capacity, you're not getting linear type of ability to handle load and request, okay? All right, So again, to summarize, vertical scaling, it's linear to a point. Horizontal scaling generally tends to be linear, as big as you can scale it, okay? And the other key thing is that horizontal scaling is also elastic. So getting back to what we were talking about earlier, okay, how do we get elasticity in our environment? All right, so let's dive into enterprise cloud patterns, and there are quite a few of them. There's actually like 20 or 30. Does anybody remember this TV show, by the way? Yeah, okay. I was working at a startup when this TV show was on, actually right here in Atlanta. The startup was called Tripling O. And I had to stop watching this because it was way too close to real life. Not joking, so anyways. Right, so you might be thinking, well, there are lots of code patterns already, right? There's the decorator pattern and the observer, et cetera, et cetera. All these are low-level code patterns. So what are these enterprise cloud patterns? These are more higher-level patterns, not low-level patterns. But if you're familiar with some of the patterns I just mentioned, or you use them at work or whatever at the code level, you'll see how they translate directly into high-level systems architecture, okay? So you won't be completely lost as we go through this. All right, so there are a number of different categories. The one that we're going to talk about today is the third one, data management, right? So I also have a presentation online that's around design and implementation patterns, but today we're going to focus on data patterns specifically. All right, so the first pattern that we're going to talk about is caching. Okay, how many people use caching in their application, out of curiosity? Okay, pretty much everybody. So this will be fun. So we have a lot of people that already use caching. Let's see if I can give you information that you don't already know. Hopefully I can, okay? So what's the primary purpose of having caching? It's performance, okay? But I also like to think of caching as a way to reduce resource utilization. Okay, because for example, if you have a database and you're always pulling the same 10 records from that database, does it make sense for you to query that database every time to get those 10 records? No, of course not. What you want to do is you want to cache them. So what you do is you put less pressure on your database when you do that. So it's also a resource utilization thing. Okay, so, and again, I apologize for this badly drawn diagram. I think it gives it more of a rustic feel than a fancy diagram, okay? So, all right. So this is basically what caching is, okay? So you have an application, the app says, I need this data. Is it in the cache? No? Okay, I'm gonna go to the database and I'm gonna populate a cache with it, and then that will get returned to the application, okay? If the app goes to the cache or asks the question, I need this data, is it in the cache? If it is in the cache, well, we'll just pull it out of the cache and the data will get returned. It's a very simple concept in theory, but in practice, everyone who's done caching knows, is enormously complex, okay? So, and that's why I have this slide here. The two biggest problems in computer science. Number one, naming things, right? Do not use foo or variable x in your code, of course. The other difficult thing in computer science is tuning a cache, right? So there's more, but those are the two big ones in my opinion. Right? So when we think of a cache should be much faster than querying a database. At least an order of magnitude faster, if not 2 or 3 orders of magnitude faster, okay? And typically the cache is smaller than your actual data source. Right? Again, that will depend on your application, but there's not a rule of thumb for how big your cache should be. It should be dependent on your app and dependent on your load and stuff like that. Okay, so when we think of caching strategies, most caches use both. Let's we already talked about this, a couple of other things, but let's jump ahead a bit and let's talk about two different types of caching. There's what we call active caching, which is right through, and then there's lazy caching, which is known as the cache aside pattern. So we have two sub-patterns within caching. So let's get into this real quick in a couple of minutes, right through cache aside. All right, so cache benefits, we talked about this already: read performance, reduce load on database, and improve overall performance. Oh, now this thing is up, great. All right, so one of the major problems with caching is consistency and stale data in your cache. How do you manage something like this? Okay, so typically when we think about this, if we have a cache miss, we load from the data source, and if the data is updated in the database through some other path within your application, what do you have to do? You have to do cache invalidation. That means you've loaded something into the cache already, and then something over here changes that data in the database, Now you have to go into the cache and you have to say, hey, this is no longer valid, what you have in the cache. So at that point, you have a decision to make as a developer. Do you just invalidate the cache and do lazy loading of that data, right? So this is what we talked about a couple of slides ago, right? This thing, right? This thing, oops, I went too far, didn't I? Helps if you look at the screen. Okay, right. So when we have a cache invalidation, so you pull some data, it's in your cache, something over here changes it, what do you do with the data that's in the cache? We have two strategies for that. The first one is you say, okay, I've changed this data, I'm just going to go ahead and push that into the cache. Okay, so that's what's called a write-through or active cache. And then you have cache aside, which basically means you go to the cache and say, okay, this object or this bit of data with this ID is no longer valid, just dump it. And so what happens in that case is when the app needs that data, it will go pull it and then populate it, i.e. it will do it lazily. Okay? So, talked about this. Let's get back to where we were. Okay. So the other question around building out caches is, what do we do to prime the cache? So say you restart your entire system, or your application tier at least. Now your cache is going to be empty, most likely. So do you want to go ahead and start populating your cache as soon as you bring your app up? Or do you want to just go with a lazy strategy and let that cache get populated over time as requests come in? Okay, so as a developer, this is something that you have to decide for yourself, right? Or depending on what your team thinks about how the app should perform. Because if you use a lazy caching strategy, what happens is that when you first start your app up, you're going to see very, very high load as that cache gets populated, and you're going to hit your database quite a bit. So what a lot of people do is they use this strategy of pre-populating the cache whenever there's some kind of event, whether you restart your app server or you're doing like a big data load from somewhere or whatever it may be, okay? And what a lot of people do actually is instead of having the app itself do that, you can use an external process that populates your cache. So then you can trigger that external process to update the cache whenever you restart the system or you've loaded in a bunch of data or whatever. Okay, so this is getting into like more advanced caching types of techniques. All right, so I'm not going to talk too much more about cache, but we'll reference it in some of the other patterns that we talk about. So next thing I want to talk about, we're going to spend quite a bit of time on this, is a stateful versus stateless design. Okay, now does everybody in the room know what stateful versus stateless design for architecture is? This is not necessarily a cloud pattern. Does everybody know what that is? Okay, I see a few maybes in the audience. Now, when we typically build an application, it doesn't matter what platform you're on, right? So let me just throw out some, or ask some questions. How many people build stuff on Rails? Okay, oh, more than I expected. Node and JavaScript? Okay. Python and Django? I don't know. Python and something, whatever, okay. Anyone, for the Java devs, you maybe use Spring Boot or Java E? Okay, got it. All right, so the way that we typically build an application, whether it's in Rails or in Django or Spring Boot or whatever you're using, is historically we've always looked at this from a stateful design perspective. So what that means is that when you're building an application, and I'm going to use a very simple example, right? And everyone will know this. Right? So you're building an app, the user needs to log in. Okay, so the user logs in through their web browser, and then what you do on the server side is you create some kind of session object that keeps that user's information in active memory on the server. So if you're using Rails, it just magically happens underneath the hood. If you're using Django, again, same thing, or if you're using Spring Boot, you basically just say, I'm going to keep a session object for this user's login, and then you'll stuff data into there, whether it's things that the user has in their shopping cart or their profile or whatever it may be. But you keep it in active memory because you don't want to always have to reach into the database to go get that information. We talked about caching, and we talked about how we don't want to hit the database too much because then we'll overwhelm it, right? So we use a stateful design. Okay, the problem with having a stateful design is that now that this instance of your application process has that user's information in it, you always have to go to that same server, right? You may have 10 different instances of Rails or Django or your Spring Boot app, but what we do is we configure something called sticky sessions. So you have some kind of advanced piece of hardware up top that says, oh, that's this user, I'm going to send that to server A. Oh, it's that same user, I'm going to send it to server A, okay? So we keep state on the server. And that helps our app run much, much faster, which is great. Okay. However, the problem is now that we have that stickiness configured and we're keeping that app data, or that, let's say, user data in this case, on a specific instance, we've actually created two problems, okay? The first problem is now we're using more active memory. So your app may be fine with like 10,000 concurrent users, but what happens if you go to 100,000 users? What do you do then? Well, you just add more nodes, okay? That's great, but is that necessarily the best way to design something for an elastic cloud scenario? Maybe is the answer. I did say there were trick questions, right? So the answer here is maybe, okay? It depends on your app. However, what we want to do when we go to the cloud is we want things to be as stateless as possible, because stateless design is inherently more elastic and more scalable, right? And in software architecture, we have a saying that nothing is free. Okay, so if someone tries to say, hey, you should use this thing, it'll solve all your problems and there's no penalty to be paid for it, that person is lying to you, okay? There's always a trade-off. Software architecture is a series of trade-offs. Doesn't matter what you're doing, there's always some kind of trade-off. So when we go from stateful to stateless design, we're making a series of trade-offs, but depending on your app, those may be better trade-offs than the alternatives. Okay, so let's talk about that. Right, so we talked about this already, right? What does stateful look like? Short-term data, right? Almost like a cache, right? And stateless design looks more like this. Okay, so let me flip back to stateful so you can see what this looks like. And this is what stateless looks like. Okay, so now you have some kind of external data store right here that keeps your short-term data. And the key thing there is that it's not in process in your application. It's over here somewhere, okay? So that means that now when you configure a node or a server in your app, it can always be small-ish, or at least smaller than the stateful design. You can have less CPU and you can have less memory because you're pushing that stuff over here somewhere. And that's where you keep the state, okay? So I'm gonna ask you a question. What are some of the trade-offs from going from an architecture that looks like this to one that looks like this? Okay, anyone want to take a few guesses at this?
You're able to break up your application into smaller pieces, so developer teams don't have to, you can actually unbreak that monolith and use microservices.
Okay, that's actually a really good answer. So the gentleman in the back said you can have smaller deployments, smaller bits of code, smaller apps in general. Okay, that's a good answer. Okay, what are some of the other trade-offs with going from this to this type of architecture?
Now, whatever objects you want to cache, they have to be serialized and put in Redis or something like that.
That's
so
right.
One could be just a JVM memory object, now has to be some JSON stuff that's there, serialized, deserialized, and convert possible.
Right, so you hit upon probably one of the most important points is that when you externalize your state into some other service, then you have to be concerned with serialization and deserialization of that data. And when you do that, what's the other penalty that you pay? Performance, right? So it's performance. But again, what is the trade-off in terms of having that lightning fast performance with an in-memory, in-process data object as opposed to one over here? Okay, it may be small or minimal, but can your system or can your users, are they okay with it, right? Is a 700 millisecond response time okay, or do you need a 300 millisecond response time? I just made those numbers up, but you get the idea, okay? All right, so again, state affects scalability. We talked about this already, and not storing state on the client. So internal state is within the app itself. External state is outside the app's memory, okay? So just doing a bit of a review. I'm sorry that's cut off at the top. Now, one of the problems with having a stateful architecture is say that you have 10 nodes and one of those nodes goes down for whatever reason. What happens to the state that was in that node? It's gone, right? So the user may be through some kind of complex process where they're doing like a 15-page wizard to fill something out, I don't know, whatever. that server goes down, they potentially have lost all that stuff that they've entered in there, okay, and that's a problem. So when you externalize this state, you have the added benefit that you don't have to worry about that because it'll just reach out to this external resource and go grab that data. And of course, you have redundancies for that external state thing that you're using. That external state thing could be something as simple as a database, or it could be something a little bit more elaborate like Redis, for example, right? A lot of people use Redis to implement this external state type architecture. How many people are using Redis out of curiosity? Okay, so there you go. And I'm sure you folks are using Redis for external state storage, right? Okay. All right, so we talked about app stickiness. State is not lost. Of course, we are trading off having that stuff in memory to having something that's outside of our memory. So it is a little bit slower, but it gives us the ability to do long-term higher horizontal scaling, okay? Because now that we've moved this state over here, we can manage exactly what compute and data and storage resources we need for that data layer, i.e. if you're using something like Redis, you can scale up your Redis even more, right, to get more scale. And then your app instances can be very small, or let me rephrase that. They can be smaller because you don't need as much memory and compute power over there. So now you're getting a double whammy of extra scale. You can scale up your data tier individually from your actual app tier, okay? And of course, there's some trade-offs when you do that. The main trade-off when you do that is, aside from the performance, is what? What have we also traded off when we do this? What's that? Exactly. Now we've made things way more complex. And that is not a trivial thing. All right, so we have to be cognizant of that when we're designing an architecture. Because it sounds like fun. It's like, hey, let's use this cool tool called Redis. It keeps everything in memory. It's like lightning fast and blah, 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 blah. But now you have to consider serialization and deserialization from your app into Redis, okay? That means you have to write code to possibly do that. I know there are helper libraries and tools and stuff like that to help you, but you still have to be aware that that's what you're doing. Otherwise, you'll run into problems later, right? What happens if your domain model, i.e. the objects that you use to represent the data for whatever business app you're building, what happens as that grows in complexity over time and you add more objects and your business people want more features? Now you have to think about, okay, how are we going to put that into Redis? Who's going to manage the objects that will do serialization, deserialization, et cetera, okay? All right, so it's great at horizontal scaling if that's what you need, but it does add complexity. We've already talked about this, so I won't go into this too much more. Okay, we talked about consistency and stuff like that. So let's take a quick check here, right? Because a lot of people raise their hands with that they use. For those people who raise their hands that they use Redis, how many people you think it works great? Don't have any problems with it? Just oh, let me rephrase it. Do people have any issues, or whether it's small or big issues, with using something like Redis? You kind of went like this. So, well, just out of curiosity, what was it?
You lose some of the benefits of using a traditional SQL server.
Okay, right. So the response was you lose some of the benefits of using a traditional SQL server, i.e. the queryability of your data is not as good as a SQL server, okay, or any kind of SQL-based database. So let's actually talk about this really quickly, right? So you can see at the bottom, if we go for external state and we do either a SQL database or some kind of memory data store like Redis, and again, I'm going to try to refrain from mentioning the specific ones for like AWS and Google Cloud or whatever, right? Just keeping this a little high level and a little conceptual, okay? So a SQL database is durable over time. That means if for whatever reason your data grid goes down, you can restart your database or bring your database back up. It'll pull everything from the write-ahead log, and you will not have lost any data, maybe a little bit of data if you had a crash or something, okay? SQL databases generally tend to be simple in terms of architecture, but of course SQL databases are slower, and all your complexity is in the app and database tiers. So you only have two tiers that you have to contend with for complexity, okay? So if you use a memory data store, it's maybe not as durable, right? What happens if your Redis grid goes down? Where does that data go? Can it be loaded from some kind of file backup that it's writing to or whatever? I don't know the answer to that. It depends on how you configure Redis, right? Okay, you have a more complex architecture because instead of only having 2 layers, now you have 3 layers of your architecture. So that's something, again, not something to be just said, oh, it'll be fine. It's like you have to think about that. Right? Am I adding this complexity, and is it worth adding that complexity? Okay, but it's definitely more scalable. Is it more expensive? Maybe, right? You might be actually saving a lot of money by not hitting your database continuously. So, there you go. And there's actually, the folks at Google actually came out with something really interesting, well, Google Cloud Platform specifically. A couple of months ago, about 2 or 3 months ago, they rolled out something called alloted, which is a Postgres-based advanced horizontally scalable multi-region, et cetera, database that's based on Postgres. So it's straight SQL, more or less, but they essentially went in and made the open source Postgres to be much more advanced and give you a lot of features that, well, frankly, that Google Cloud was missing, but you kind of get those features with AWS Aurora. But in my opinion, AWS Aurora is not as advanced as alloted from Google Cloud. But we can talk about that over lunch if you like. Okay. All right, let's see how much time we have. This is probably the last one we'll have time to cover before we have to break, which is in 4 minutes. So another data pattern that I like to talk about quite a bit is materialized views. Okay. How many people use materialized views in their application? Okay, great. Only one person does. What's that? Okay, that's because you use Postgres. Well, this is not specifically about Postgres, actually. Okay, this is great. Now, we actually hit on a pattern that most people have not heard of. So you'll actually learn something new in this presentation. Okay, so like you were saying, it's not the same as SQL views. Okay, what are materialized views? Right, a standard view in a database is a name query that pulls data from tables. Okay, that's what that's when we think of a view. That's what it is. Materialized views are different. It's not just for relational databases. Right, so let's think about what this means. All right, so we have an orders table on the left and then an items sold materialized view. And one of the things that you can do in a materialized view is you can have something like aggregates. Okay, so you can see on the left side here, we just have, the item, shirt, shoes, the amount, but on our items sold materialized views, I can say, how many shirts have I sold today? And I can say, okay, I've sold 2 shirts and the amount was 60. How many shoes have I sold? 1 pair of shoes amounting to $50, okay? So you don't have to, materialized views are not just for aggregates, but you can use them for aggregates, okay? They're super helpful, again, depending on what you're building, right? If you're building a shopping cart, you need some kind of console, or sorry, a shopping application, and you need some kind of console where your manager at a store or someone running operations can see like what inventory is like. It's a really good way to use that, but there's actually more advantages to materialized views than just aggregates, which we'll talk about in just a second, okay? So data is stored once and retrieved repeatedly. So this kind of sounds like a cache. When you use a materialized view, it can almost feel like a cache. It is a cache in a way, okay? So we have this ability to offload frequent operations from the database into something that is a materialized view, okay? But again, this is like a cache. It can have its own store, so if it goes down, you can bring it back up without having to like repopulate and stuff like that, okay? Now, when we build out a materialized view, you do need to have some kind of trigger mechanism, whether it's in code or in some kind of infrastructure that goes and populates that materialized view, okay? So what that means is, say that, going back to our shopping cart example, a user buys a shirt, okay? Now we have to go and update that item sold materialized view. How do you do that? That's a good question, right? Depends on your application and what you're using to do it. You might actually write something in your app that says, okay, go send this to the materialized view and let it know that someone has bought a shirt for $50 and it will go and update its materialized view so your console is up to date, okay? So again, materialized view needs to be updated when data in the data source changes, okay? So materialized views are not good for when data changes quickly or you need strong consistency. So strong consistency is something that you may or may not be worried about depending on what you're doing, right? But there can be a lag in how quickly your materialized view gets updated. So it's just something to be aware of, okay? You might be able to tolerate that your materialized view is a second behind or a minute behind what's in the actual database, right? And that might be fine, right? I would say that in most cases, when I say that, it may sound like I'm crazy. It's like, why would you want stale data, right? That doesn't make any sense. But if you think of business cases, I would say that 90 or 95% of business cases are okay with a materialized view or some kind of view into your data having a little bit of latency in it. You just don't need that up-to-date information all the time, okay? So for a good example of this actually is Amazon. Like when you go to buy something on Amazon, you click on, okay, I want that pair of shoes. You click on it and you say, okay, add to cart. And I don't know if you've ever noticed this, but sometimes from the time that you add it to your cart to 5 or 10 seconds or a minute later, when you go to checkout, what happens? Those shoes are no longer available, okay? So that's a case where, it's basically a lag, but your user's able to tolerate that. They'll be disappointed, obviously, but what's the solution to something like that? Well, you could lock that specific inventory until the user checks out, which is what a ticket system does, right? So if you go buy tickets for, I don't know, let's say Atlanta United Soccer, and what do they have? They have a little timer in the top right of the screen saying, we're holding these tickets for 15 minutes for you. But to do that as a developer, you know that that's a whole lot of work right there to make that work and make it consistent and not have people go into a rage because they think they have a ticket and then something goes wrong, right? Anyways, you get the idea. Okay. So the other thing about materialized views is that you have to make sure that your data is shaped and sized appropriately. So the shape of the data means what fields are you including, what different types of objects, et cetera, are you using in your materialized views, and how much of that data do you keep in a materialized view? Because a materialized view should typically not be anywhere close to as big as your actual entire database, okay? So what we do for materialized views, the way that we kind of think about them also is that we create them for specific use cases, right? We don't just say, hey, let's just mirror this entire user table or this entire item table. We say, this is what we specifically need. This is the problem we're trying to solve. We want to have possibly aggregates in this, and we want to be able to access this data quickly without putting a lot of pressure on the database and not have to do long queries, et cetera, okay? But again, it's trade-offs. You might have lag. You add extra overhead to your system because you have to go and push this stuff into a materialized view, okay? All right, so we talked about aggregates. We can have calculated fields and transforms. And of course, materialized views should be easily recreatable. That means you should be able to run a script or some kind of process that goes and repopulates that materialized view if it goes down for whatever reason, okay? Or you need to scale it up and add some more stuff. Now, do I have another diagram here? This is a Kafka example, okay. So I'm gonna use a couple examples here. How many people use Apache Kafka at work? Okay, how many people don't know what Apache Kafka is? Okay, few people. All right, so Apache Kafka is what is commonly referred to as an event streaming platform or data streaming. So instead of, or what I think the nomenclature they use for it is data in motion. So the idea is that you have this funnel of data coming from something. It'll be sensors, or like you have a truck out in the field that's doing some diagnostics on like your gas meter or something. So there's this data streaming into your platform, and you essentially work with that data as it streams in. You can do a number of different things with it, okay? And part of this presentation talks about CQRS, or command segregation. I'm gonna totally get this wrong. CQRS, command, query, responsibility, segregation. Is that right? Okay, I'm surprised I remembered that. Anyways, so a lot of people use Kafka for that, and if we had time, I could go into CQRS and make a case for not doing CQRS and using materialized views instead, because materialized views are about 100 times more simple than doing a full CQRS architecture. But again, I'll go into that rant over lunch if you're interested, okay? So let's think about an example from Kafka here. So we have parts. We want to know what the average of those parts is, so we can do a query against a Kafka data store and say, create this materialized view for me. Okay, so this is a Kafka specific example. So materialized views can be anything. You can have materialized views for databases. You can have them for something like Kafka. You can even create a materialized view for your Redis cluster if you want, right? So there are lots of different options there. Okay, let me see what the next example is. This one's in Java, but I'm sure you get it, right? You can see on the left, what we're doing is we're creating a materialized view in a Postgres database, and So what we say is create this materialized view, sales summary with the seller number, invoice, and then the sum of all the different amounts, et cetera, et cetera. And then we create some indices to make lookup faster. And then the way that we translate this into code is we create an object that specifically references that view so we can easily go and grab that data within our code, right? And again, this example is in Java, but if you're using Rails or Python or JavaScript or whatever, you get the idea here, right? This is just a simple container object, or what we would commonly refer to in development as a data object that mirrors that materialized view, okay? All right, and with that, we're at the end of time. I'm just gonna quickly flip through the rest of this, so if you want to go watch the other 4 hours of this video, it's online, you'll find it on YouTube. I spend a little bit of time talking about, actually I'm not gonna flip one by one through this, streaming versus message queuing. And so that's a lot of fun, right? So there's some more badly drawn diagrams in here. Replica sets, which is a way to speed up your database without using something like Redis. And you can do this like very easily in Postgres, for example. And then I spent a lot of time on sharding and how to do sharding properly to get the most out of your data tier. And then the last one is on command query responsibility segregation. I actually did get that right, so I'm very proud of myself. And talk about different things. And then this is the most advanced one that I go into. It's called the compensating transaction pattern. And especially when you do cloud type of things, and especially when you do stateless type of design, you have to really think about, I think it may be time to do compensating transactions so that we can get more horizontal scaling and more velocity for the things that we're doing rather than using distributed transactions. So one thing I will note in closing real quick, right, so there's a lot of stuff there. I'm not going to talk about the specialized open source tools. The short answer is don't build this stuff yourself. Just use something off the shelf, okay? Don't be crazy. So you think you might be smart, but there's nothing like like hundreds of people working on an open source project to build something like Apache Pinot or Kafka. So, all right, so finally I'd like to say if you do want to have this entire 4-hour workshop type of thing at your company, part of my job is to come to you and to talk to you about this stuff. So please reach out to me on Twitter or by email, and I'd be happy to do that. And thank you for coming, and I apologize for running a bit over. I know it's lunchtime, and I don't want to get bad reviews, please. So, okay, thank you everyone for coming.